So in today's lecture, we're going to look at the finite element discrete equations. And, well, this is the outline. There are two ways to get to the discrete equations. In the nonlinear mechanics class, we saw one of them. I like this idea of looking at local equilibrium of one element. Since the whole system has to be in equilibrium, then obviously you can isolate any part of the system that should also be in equilibrium. So we can look at assembling the global system by just looking at the equilibrium of one element, and then we use this so-called finite element assembly operator to construct our global matrices. We're going to look at some examples, and then also how we are going to solve the discrete system of equations, because there are actually a couple of ways to do it. Okay? All right. So if you recall, we had the Galerkin projection. From the variational statement that we had of equilibrium, we were living in an infinite dimensional space, and then we said, well, now that we do the Galerkin projection, we're going to choose finite dimensional spaces, right? And there are many such spaces that you can think of. For instance, if you're familiar with the Rayleigh-Ritz method, you would choose for some functions that are global. They are not local like the finite elements, but they are global in the domain. Like for instance, trigonometric functions, and so that would be a finite dimensional space, because normally you would choose a number of them, right? Certain series of signed functions with different arguments, but then it's still a finite dimensional space because the number of coefficients that you solve for are just a handful of them, right? Well, the finite element method uses linear or quadratic polynomials at best, right? The standard finite element method. And so what we're going to do is we're going to choose both our test function here and our trial solution. This is our trial solution. Remember now, because we are in a finite dimensional space, we are going to call this the trial solution. So it's not going to be perhaps the exact solution of the problem. So we call it trial solution. How good it is? Well, again, we may know some information about the exact solution. We can compute errors, right? And if not, well, we hope for the best. Hopefully, the tools that you build in this course will allow you to understand how good this trial solution is going to be. So we choose those from a finite dimensional space, and in particular, we use finite element spaces in this for these problems. And so imagine that you have your finite element discretization of the bar. So here I'm showing you 4 elements, and those are the shape functions that we normally use. Those are the linear, they are called hat functions. Some others call them roof functions. But the idea is that at each node of a finite element, the function has a value equal to 1, and it ramps linearly to 0 at the other node, right? So if I isolate, for instance, element 2 has 2 shape functions that are non-zero in that element, phi2 and phi3, right? And these functions are very interesting. They have interesting properties. And then, of course, we're going to talk about those properties in a minute. But those functions for each element can be written as you see here, right? Very simple. You can very quickly check that the function is indeed equal to 1 at the location of the corresponding node, and equal to 0 in every other node, basically. And we are going to essentially represent our test function and our trial solution, if you see here, these two, in the same way, right? We are using the same number of nodes for the discretization, and this leads to the so-called Bubnov-Galerkin projection, as we described in the previous lecture, right? And so let's talk a little bit about these properties. One very interesting property of this function is the so-called partition of unity property. The fact that at every single point in the element, the summation of all those functions are equal to 1. That is the so-called partition of unity property. And this property is, of course, interesting, not so much perhaps in standard finite elements, but when we move to more advanced formulations, this is a very, very important property. Also, they have the so-called Kronecker delta property. That basically means that if you take one shake function, right, if you evaluate that function at the corresponding node, that is equal to 1. If you evaluate that function at every other node, is equal to 0. And you can express that function like this, right? Phi I at xj is the Kronecker delta. That's why it's called the Kronecker delta property. Normally, in standard finite elements, we associate functions with a node. And this is kind of interesting, right? You're saying, if you notice here in the previous slide, if you notice here, we have, for instance, this node here. This is going to be the second node of our mesh. And we are associating that function phi2 to that node, right? And we do that because in the end, the degree of freedom that is associated to that node is going to represent the displacement field. In reality, right, this function is actually non-zero in this entire domain, right? These two elements, right? And so in more advanced formulations, we can no longer say that we can associate one function to a given physical location of a node, but to a region, right? That region in finite element method is called the support of the function. So I can say that phi2 here, right, has a support that involves these two elements. Okay, but to make things simpler, at least for the H version of M, we say, well, this function phi2 is going to be associated with that node here, the second node of a mesh, right? And again, we do that because in the end, the degree of freedom associated to that node is going to give me physical interpretation of the displacement field at that location. So that is a consequence of this second property, the fact that the Kronecker delta property, the shake function is equal to 1 at the location of the node, right? And every other function is going to be equal to 0. That basically means that the degree of freedom that is associated to that nodal location is going to represent the displacement field. So our degree of freedom has a physical interpretation, right? And this happens in standard FEM only. When we move to more advanced formulations, right, this may not hold anymore. In particular, when we look at more advanced formulation where the displacement field, for instance, is written as a series of additions of different quantities, then we lose, for instance, the partition of unity property. We use the Kronecker delta property, and so that physical interpretation of the degree of freedom no longer holds, okay? Okay, but in HFEM, we are going to always we're going to use the so-called Lagrangian elements, and so we have these two important properties. Again, partition of unity, meaning that all functions sum up to 1 at any location in our domain, and the Kronecker delta property. Okay. As I said in the nonlinear mechanics course, if you remember, someone asked me, well, is there another way to get to the global system of equations? Yeah, well, this is what we're going to do here. If you recall the Galerkin projection, we wrote, well, find the function u such that the bilinear form is equal to the linear form for all test functions in a given space, right? Well, we can write that function here, right? This is our abstract form of equilibrium. And if I plug in now in that bilinear form, here I'm plugging the test functions, and here I'm plugging the trial solution, then you see that we can start playing around with this equation, the bilinear form and the linear form, right? So by plugging in the trial solution and the test function, we can write it like this. Of course, the has to be or has to be equal. So the bilinear form equal to the linear form for all test functions. The moment we choose the discretized version of those functions, then my statement has to change into it has to be valid for all wi's, right? Because wi's are the coefficients that are unknown. Let me go back and explain that a little bit more. The moment I write my test function like this, right? If you notice, there is a part that I know, which is the shake functions, and there is a part that I do not know, that is the coefficients. So the for all test functions in a given space is going to translate in for all the unknown coefficients only because the part that I know is already known. Okay? That is why I can write this equation like this, where this seemingly bizarre statement at the end means, well, from the test functions, the only part that I do not know are those coefficients. So this expression here has to hold for all coefficients that are, again, just coefficients. Those are real numbers. So working a little bit on this formulation, you can basically pull out the coefficients. Those are constants, so they are not, you can take them out of the integral. If you recall, the bilinear form is just basically an integral. The same with your linear form, right? Of course, this is in abstract form, so those linear and bilinear forms are going to change depending on the problem that you're solving, right? And then, but we can take, nevertheless, the coefficients out of the integrals, as you see here. And then we can essentially group all the terms that are independent on my test functions. And so the fact that this equation here has to be equal to 0 for all these coefficients wi, that basically means that in order for me not to get the trivial solution, which would be having these guys equal to 0, all of them, then this whole expression here has to be equal to 0. Yeah, and that is essentially the way that we get rid of the coefficients of the test functions.
Is this a matrix statement or is this still?
Not yet, but very nice observation that, of course, this eventually is going to lead to my matrix statement because, well, if I now take, for instance, this expression here, right? Since the if equation is 0 for arbitrary wi, for wi not equal to 0, we must have, well, this expression inside here is going to be 0, right? But this is again, one of the n equations that I'm going to build. And so we can write, for instance, the if equation like this. And if I call this element here ki1, and this one is my ki2, you quickly see that I'm essentially showing what are the components of my so-called stiffness matrix here. And then on the right-hand side, this is going to be the if component of my force vector. Okay? So obviously, this expression here leads naturally to my discrete system of equations that I can simply and very compactly write as Ku equals F, where K is my so-called global stiffness matrix, my U is my global degree of freedom matrix that only in this case we can also call it the global displacement vector. And again, my U. But again, this is just a consequence of the fact that I have this Kronecker delta property where I can associate the degree of freedom with the displacement field at the location of the node. So only in this particular context, I can call my global degree of freedom vector my global displacement vector, okay? And I want to emphasize this because when we move on to more advanced formulation, even not so advanced, like whenever we start talking about the PFEM, right? Then you will also realize that my global degree of freedom vector no longer holds the physical interpretation of the displacement field. Okay? So this is a very important distinction. Okay, so K, F, and U are the global stiffness, force, and displacement arrays, respectively. I call array because, well, one is a matrix, the other one is a vector. They are all arrays. Okay? Okay, so this is, yeah.
When you set up the trial functions, you
Yeah.
use the index I.
Yeah.
Then here you use index J for the displacement. Can you explain why that is?
Yeah, because, well, the idea is to have, in the end, some dyadic product. So I need two indices, right? If you notice here, I also use the property of the symmetry, because normally I write the bilinear form as this is going to be my trial solution, but I put the test function there instead. So I actually change that. Obviously, if I have I and I, it makes no sense anymore because then I don't get to form a matrix. In the end, what I need is a dyadic product between two vector components. That's why I take different indices. Yeah? Yeah, so this is basically one way to form my discrete system. it's not the only way. If you recall the nonlinear mechanics class, we also obtain the same thing by just isolating equilibrium of a single element. So if I now look at the element level, right, if I isolate one simple element with coordinates xi and xj, right, and I write my variational or weak form of equilibrium, again, you can see this from the abstract point of view as the bilinear equal to the linear form for all test functions, or you can simply write the variational form of equilibrium, and then you write it like that. Everywhere you see a W in the variational form is changed to a WH, meaning that I'm already at the finite dimensional space. This is already the Galerkin projection. And so we write it like that. This is just the local equilibrium of one element, right? Well, if I now replace those two by what they are, right, I can write it in very simple matrix form like this. So my UH is my phi vector multiplied by my U vector. Again, this is like a row vector. It's going to be a 1/2 because in this element I have only two non-zero shake functions, right? And this is my local degree of freedom vector, right, or displacement vector. That is going to be a 2/1. So the product of a 1/2 by a 2/1 is going to give me a scalar, which is basically the displacement field along the bar. It's a scalar field. And then I write my strain displacement matrix, right? This B is the so-called strain displacement matrix because, of course, it relates displacement with strains. D phi dx, right? And then I plug all this back into the expression of equilibrium. Again, equilibrium in the weak sense because this is deriving from a variational form. Then I get this expression that you see here, right? This expression that you see here. I just simply put UH, I put it here, the same for WH, and then I put these guys here, right? And then I get this expression here. And again, now I am at one bar. In one bar, one element, right, I have only 2 degrees of freedom. That's why my weak form of equilibrium eventually turns for all W vectors, all 2-dimensional vectors, basically. Just because now I have 2 coefficients that are unknown in the bar. So the for all test functions, right, in that finite dimensional space, the moment I choose those functions from the finite element space, translates into for all 2-dimensional vectors. Okay? And well, we can quickly see and understand that, of course, this whole thing here is my local stiffness matrix. And this whole thing here, where I have also placed, if you notice, the boundary conditions for that little element, right? Those are the axial forces at the end of the element, right? This is going to be the so-called local force vector. But then you may argue, well, but then you have forces at the end of the element. Those are not really the boundary conditions, right? And that's true. The thing is that if I take the axial force at a given node from this element, from the left element, let's say, and then I do the same for the one on the right element, obviously those two are going to be in equilibrium. They are going to cancel each other. So in the end, you're going to end up having only the boundary conditions or the axial forces at the ends of the bar, right?
You impose the condition that nj of the I minus 1 element equals minus an I of the I element, right? So
No, it's not that you impose it. They have to be equal for equilibrium to hold. And so in the end, they just, you don't even consider these ones.
Does this mean that, like what we did in nonlinear, is that you first have to establish global equilibrium, and then you can basically partition everything and then see that?
You first partition everything. Then the assembly procedure is going to lead to setting up your global equilibrium, and of course the solution to the problem, if the problem is well set, is going to be unique, right? And then you will indeed find out that if you isolate any element, it's going to hold in equilibrium. You have a question?
And you say you don't impose it, but if you in the force vector set the force to 0, then that's basically the force equilibrium at a node. Then you do kind of impose it to be equal, right? If you set that force to be 0.
We don't impose it. When we talk about imposing something, it's like you're talking about prescribing a constraint to the problem.
Yeah.
We don't do that.
Okay.
Yeah. This does not mean that, for instance, we cannot add a force at a node. And indeed, the finite element method allows you to do that. So I can say, well, I want this node. Now I can put a concentrated force into that node, right? And now things are a little bit different. So then you do have to consider that into the force vector. Yeah? Okay, but in any case, you get into this local system that you can very nicely and compactly write like this. And this is my local, again, local because I'm considering one finite element is my local equilibrium to that element, right? And obviously this has to hold because I'm not interested in a trivial solution to this equation that says, well, I have to pick this guy W equal to 0 in order for this whole equation to be satisfied. Well, in order not to pick the trivial solution, I have to ensure that this whole thing is equal to 0. And that's why I get my local system of equilibrium. All right? Okay. So we did this example. Yeah, you have a question?
Yeah, so the wave function, we just use it to not have a trivial solution. Get the K equals F. Like, what are we really using the wave function for?
So if you recall, this whole business of projecting our differential equation into a space involves the wave function. Again, it is not just a function, it's a number of functions. So that's why we talk about spaces, right? The Galerkin, if you recall, the Galerkin projection, right, was essentially some sort of dot product between functions in the bilinear sense, right? Where you're saying that this weight function multiplied my differential equation integrated over the domain is equal to 0. But again, it's not a function. It's a whole set of different functions in that space. So that is why it's called the projection. That is essentially the role of the test function. If we didn't have a test function, then we cannot do this projection because we cannot set this orthogonality condition between my differential equation and an entire space of functions. Is that more clear? Yeah? Okay. Well, but then if I have the local equilibrium at the one element, then how do we get into the whole system? This is something that we're going to look up in a minute. But before that, if you recall this example from our nonlinear mechanics course, then, well, we simply show you very quickly, very simply how to get to our infamous stiffness matrix for the bar element that you have repeatedly seen in your mechanical engineering courses every now and then. That is EA divided by L, 1 minus 1 minus 1, 1. You have all seen these. But here's basically a very simple example how you can obtain that. Well, the shape functions are linear. The derivatives of these shape functions are constant. And so when I introduce all that into my local stiffness matrix, of course, everything that is constant I can remove out of the integral, and I get only this term, and this is just the length of the bar. And so you get into that expression for the stiffness matrix. A nice thing about being able to visualize this is, of course, I can now plug anything I want. And I can assume that, for instance, E or A are non-constant. I can also plug different functions, and then I can see that my stiffness matrix for the local element is going to change. Okay? All right.
For this trivial solution, it doesn't actually matter to partition the bar, right? Because if you add them all together, then basically you get the same stiffness matrix out of it.
You get the same stiffness matrix, yes. For every bar, it's going to be the same.
It's particularly important if E and A are not constant over the length of the bar, because then you need
to integrate differently in each bar, and then you're going to get different values for each element. Yeah? Yeah. All right. So let's talk about how to solve this system of equations, because there are a couple of ways to do it. There is the intuitive way, and there is the easy way. Okay? So we can assemble the whole system. Now, if you notice, I use uppercase now to show the global system. So K is my global stiffness matrix. U is, again, my global degree of freedom vector or displacement vector. And F is my global force vector. And then normally we write it that K is essentially the result of the assembly operator on all these local stiffness matrices, and the same for the force vector. We call this A, weird symbol. the standard finite element assembly operator. And it is just a fancy way to say, well, we're going to take these stiffness matrices and we're going to get all those element freedom tables, their corresponding element freedom tables, right? So you are going to basically sum the stiffness matrix in the right locations in the global stiffness matrix so that things make sense. That's pretty much what the assembly operator is doing. And so you can have two ways to solve this. You can either decompose your system into free and prescribed degrees of freedom, right? So here you have, for instance, this KFF is the free part of the matrix. So all the degrees of freedom that are not prescribed are the free degrees of freedom. And then you have the PP part of the stiffness matrix that corresponds to those degrees of freedom that are prescribed, right? So for instance, a prescribed degree of freedom would be the displacement directly zero boundary condition at the left end, right? That would be a prescribed degree of freedom. So prescribed in this context means all my essential boundary conditions, right? When we prescribe the displacement, we're talking about UP. UP is the value of the displacement at that location of the node that I want it to be 0 or I want it to be 1 or whatever I want it to be, okay? And so if we now decompose the matrix like this, well, if you notice, I actually know this guy. I know UP. Those are the prescribed values. Those are the ones that I know. So I'm actually only interested in UF. So I can simply solve the first equation, right? Which is basically KFF UF plus KFP UP equals FF, right? That is the first equation. And I can simply solve that equation by inverting only the KFF part of it. Again, remember that we are never inverting a matrix per se. We're performing Gaussian elimination. We never get the actual inverse of a matrix in computational mechanics because that is more costly, right? All we are interested is in getting UF, right? Well, and what happened to the second equation? Well, we don't really ever look at it unless, right, you are interested in knowing what is the value of the reaction force, right? So this FP is the actual force at the prescribed degrees of freedom. So obviously, once I have UF, right, once I solve for the free degrees of freedom, I can solve for this equation, KFP transpose UF plus KPP UP equals FP, and then I get my reactions. But normally, yeah, this is not done in practice unless you have some particular interest in finding what the reaction forces are. Yeah?
In MATLAB and Python, when you invert the matrix,
Yeah.
does it do the Gaussian elimination?
Yes. Yes, that's what MATLAB does. So your bar, I don't know how you call it, backslash, that is exactly what it's doing. So you are never computing the inverse of a matrix, okay? You are performing Gaussian elimination, and of course there are different ways to do Gaussian elimination. And you have also different solvers. You have iterative solvers, you have direct solvers. Normally, in the end, we use iterative solvers because they are fast, but again, as we discussed, it depends also on the condition number. So if your system is well conditioned, you can use iterative solvers, and you can obtain very quickly the solution of the problem. And within iterative solvers, you also have different approaches, right? You have all sorts of different ways to solve your matrix. That is an entire scientific computer field on its own. And there are people who are still performing research on these techniques. Okay?
Finding the Gaussian finding an algorithm for efficient Gaussian.
Yeah, there are people working on trying to improve on solvers, right? You have multi-grid solvers where you are basically solving the system at different levels of hierarchy, and so you can get very, very advanced when it comes to solvers. Yeah.
Could you once again explain what an assembly operator does? 'Cause it's been
We will see that in a second in an example, and everything's going to be clear.
What does KFP represent? Is that composed of free or prescribed components or both?
Both. Those are the coupling terms.
Okay.
So if you think about an element that has 1 degree of freedom that is prescribed and 1 degree of freedom that is fixed, right? The local stiffness matrix to that element is going to have both free and prescribed and the coupling terms. Yeah? Okay, so this is one way, this is the intuitive way, right? Actually, my first finite element code I ever wrote, I was doing a PhD. I did it very rudimentary. So I was actually splitting the matrix in free and prescribed. So I actually have if loops. I had a loop and then if statements like if the degree of freedom is prescribed, put it into this matrix. If it is free, put it into that matrix, right? It was kind of crazy, right? I don't know why I did that way. When you don't know something, you try to think about the solution of a problem, but if you dig a little bit deeper, you realize that, okay, that was so dumb because there are so many other easier ways to do this. And what we normally do is we can actually modify the original system, right? So the idea is that imagine that now you write the same way your matrix, right? Now, of course, I am showing this schematically. Don't take it as all the 3 degrees of freedom are taking part of the upper part of the matrix, because nowadays with slicing, right? You have proper slicing. You can retrieve the part of the stiffness matrix that has only the 3 degrees of freedom. But schematically, let's imagine that we split the matrix like this, okay? Well, instead of doing this and solving for that, I can simply look at the matrix, right? This equation here. And again, I am interested in obtaining this guy, right? Which is the 3 degrees of freedom, right? So what I'm going to do is, well, I'm going to modify the right-hand side. So my FF is going to change to FF minus KFPUP, right? Why? Well, because I know that my UF is going to require that. It's going to require that change, right? And I'm going to set my right-hand side simply to UP, okay? And then I'm gonna zero out the rows and the columns of the prescribed degrees of freedom, and I'm gonna set all the diagonal terms equal to 1. So that's why you have here the identity matrix. This is 0, 0, and the identity matrix. And so now, if you notice, I have transformed my system of equations. I have completely removed the rigid body modes, right? I don't have 0 eigenvalues anymore. My system is no longer singular. All those are equivalent statements saying now I can solve my system, right? And I am basically, if you notice, this equation on top, right? KFF UF is equal to F minus KFP UP, which is the same equation that I have here. Exactly the same, right? And then the second equation is basically just a trivial equation that says, well, the identity matrix times UP is equal to UP, which is UP equals to UP. So we have transformed our original system of equations into, by adding, in a way, trivial equations of the form 1 times the prescribed degree of freedom is equal to the prescribed degree of freedom. That's what we did, right? And now we can solve this. The nice thing is that we don't need to partition matrices. We don't need to do any slicing. We don't need to extract parts of the matrix, which makes things complicated. We can always work on the same system, and then we can get to the solution of our problem. And for the entire vector, so the solution to this problem gives me the entire U, right? Because I also have UP there. So this is the easy way to do it. And this is the way we do it in our finite element code as well. The finite element code does not give you that part, I believe, but the reason is because we are assuming always that UP is equal to 0. In that case, that, let's say, computation simplifies, and you don't need to include that term here. Yeah?
Computationally, isn't this not good because now you have to solve a bigger matrix?
It is a bigger matrix, but keep in mind that what we call boundary is confined to a lower dimensional manifold, we say, right? So for instance, in 3D, your boundary condition would be a 2D. So that is essentially, asymptotically, that is a very, very small number of degrees of freedom. So essentially, it boils down to be the same. Computational time is not affected by that. It's a slightly bigger system indeed, but asymptotically it's the same computational time. Again, because our boundary conditions are prescribed on a lower dimensional manifold, okay? Okay, let's look at an example very quickly in the next 3 minutes so that everything becomes very crystal clear. What are we doing? How are we solving for this problem? So if you recall, we had also in nonlinear mechanics this bimaterial interface where we had our our bar, and then we split it at some point, right? And then we say, well, I'm going to assume that this guy here has some Young's modulus. This one has a different one. And then I'm going to prescribe the 0 displacement at this end, and then I am applying a force at the right end. And so I'm going to discretize this bar in just how many nodes? 3 nodes, 2 elements. Each element has different Young's modulus. And now let's look at it. And again, essentially, our nonlinear mechanics course taught you how to solve this problem so that you understand how the assembly works. So now I'm going to isolate the first element. This first element has element freedom table 1, 2, meaning that the element is connected to nodes 1 and 2, right? So I can write my trial solution only in that element as phi1, phi2 multiplied by u1, u2. Again, I have only 2 non-zero shake functions in that element. And then my strain displacement matrix looks like this. For that, it's basically the same stiffness matrix that we looked at earlier. The only thing is that now I have one value of the stiffness matrix that is going to be different in the first element than in the second element. So then my first element stiffness matrix looks like this. And I emphasize how I write it because now this is my element freedom table, 1, 2, 1, 2. And so if I look at this guy here, right, I have to look at those 2. And so this is the 1, 1 component of my global stiffness matrix. So I know where I have to place that element of the matrix. The same with this one. This is 1, 2, right? And here you notice that I'm dealing with this KFP part, right? Sir? You were asking about this earlier, right? Or who was asking about the coupling terms? Oh, you were. Anyways, if you recall, this element, this degree of freedom here is prescribed. This one is actually free. And so this is my KFP part of my local stiffness matrix, right? We do the same for the second element. So this one is connected to nodes 2 and 3, right? And now I do the same procedure, strain displacement matrix, and then my local stiffness matrix. And now I have this K2 bar because I have a different Young's modulus. And now I do the assembly operator. Again, I write down the 2 and 3 that corresponds to my element freedom table. And now I have this one here that is going to the 2, 2 location, right? So now I see that my 2, 2 location is important because since I have one shared node between these 2 elements, well, this 2, 2 location is going to receive a contribution from this element and also from that element. And so when we apply the assembly procedure, now we know that that element is shown there. Okay? This is my entire system of equations, the global system, again, after assembly, where you see in the upper left portion of the matrix, everything that is contributed by the first element. You see in the lower right component of that matrix, everything that is contributed from the right element. Here I put the reaction force, which is actually not relevant anymore because, again, I'm going to remove that. I zero out the row and the column. I set equal to 1 into that, right? Zero out, I set equal to 1. And then 1 multiplied by u1 is equal to 0 because that is the value that I want to prescribe there. And then when I solve this problem, I get the solution for the entire problem. Yeah? So this is concluding the discretization of our problem of the one-dimensional bar. We started from the strong form, we went to the variational form, the Galerkin projection, and then we saw how to solve the discrete system of equations for one simple problem. Again, from here to assembling 1 million elements is just a matter of bookkeeping. There is nothing more to it, okay? So we stop here, and then in a few minutes we are going to start with heat conduction.